to welcome you all to the generic talk series 41 organized by RMK College of Engineering Technology, Tiruvallur. Today's the session is on the topic scheduling multiple real-time periodic task graphs on heterogeneous systems. This is highly relevant and important area, especially in the context of modern embedded systems, cyber physical systems, and heterogeneous computing platforms. We are delighted to have with us Dr. DEVARAJ as today's resource person. Dr. Rajesh received his BE degree in the Electronics and Communication Engineering from Azhaggappa Chettiar Government College of Engineering Technology, Karaikudi in the year 2008. He began his professional career as an FPGA or ASIC verification engineer at HCL Technologies, Chennai, where he worked from 2008 to 2012. He then pursued his MTech and PhD dual degrees in computer science and engineering at IIT Guwahati and completed them in 2018. Since then, he has been associated with Nvidia Bengaluru, where he is currently serving as a senior system software engineer in software Tegra team, focusing on kernel mode device driver development of GPUs. His research interest includes real-time systems, scheduling for heterogeneous platforms, and energy-aware cyber physical systems. He is also an active contributor to the research community, serving as a member of ACM TODA's Distinguished Reviewer Board for 2025 and has reviewed more than 850 research articles for leading publishers. Rajesh, we are indeed honored to have you with us today to share your expertise and insights on this significant topic. I'm sure this session will be highly informative and beneficial to our faculty members, students, and all participants for joining through the RMKCT YouTube channel. On behalf of the management, the principal, and the Dean Research, Dean Academic, and all the head of the departments, and the faculty and the students of RMK College of Engineering Technology, I extend a warm welcome to you. Now, without any further delay, I request you to take over the session. Thank you.
Okay. Thanks, ma'am. Thanks for the detailed introduction, madam. Yeah, I will share my screen and go ahead, madam.
Yeah.
Ma'am, can you see my screen?
Yes, I can see.
Okay, ma'am. Thanks, ma'am. Thanks for the confirmation. Yeah, so as madam mentioned, so today's topic for the presentation is scheduling multiple real-time periodic task graphs on heterogeneous systems. This is one of the research works that I have conducted a few years ago, along with all my faculties in IIT Kharagpur and then IIT Guwahati. So this is a very high-level topic of scheduling multiple applications. So before jumping into the details of this particular problem statement, first I want to provide a brief overview of what is a cyber physical system, and then from the general cyber physical system point of view, how we are deviating to the automotive cyber physical system. From automotive cyber physical system, what are the internal components? Specifically, what are the applications are going to be executed on this automotive cyber physical system, and what is the underlying hardware configuration? So those internal details we will take a look, and then this high-level problem statement is deals with the multiple periodic task graphs. Suppose first we'll start with single task graph. Suppose given a single task graph, how do we schedule that in single task graph such that we are satisfying the application level requirements as well as the underlying hardware platform requirements. And then while generating the scheduling solutions, there are multiple ways to generate a solution. Either you can generate a solution in terms of an optimal way. Optimal means if that is the best possible solution you can obtain. And then there's a crude solution, but there's a trade-off. For example, if you take the case of a digital design, we have a K-map as well as the Queen-Migletsky method. Okay, the main difference between these two methods is that K-map is a kind of a visual approach, which is a kind of a heuristic. Heuristic means it is not guaranteed to provide the minimal Boolean expression. Okay, but the Queen-Migletsky is a step-by-step method, which provides a guaranteed solution, and it's always the best possible solution. But we understand the trade-off, right? So if you want a quick solution, we will go for the K-map. But if you want a best solution, we will go for the Queen-Megg scheme. Okay, so that is the difference between a heuristic and optimal solution. Okay, so for this problem statement, specifically scheduling these applications on automotive cyber physical systems, we will specifically focus on what are the different types of strategies. First, we will start with the optimal approach. Okay, and we will discuss how to derive optimal approach, and then what are the challenges in this optimal approaches, and then the motivation for going for a heuristic, then how to develop a heuristic. So that we will discuss, and then from a single application we will move the discussion to the multiple applications. Okay, and then what are the additional constraints in the recent time with respect to the platform. For example, platforms we know, right? So specifically platform means I'm referring to the hardware platform containing CPUs, GPUs, FPGAs. So these platforms over the years has a multiple computation demands, and then they support multiple features like DVFS, dynamic voltage and frequency scaling. So provided these knobs in the platform, how do we tune those knobs so that application also completes on time, as well as the objectives like energy, reliability, and thermal constraints are satisfied. So this is the overview of this presentation. I'll first start with the definition of cyber physical systems. See, at a high level, we already know the term embedded systems, which was used so frequently over the past few decades. So now recently we have started using the term cyber physical systems. So cyber physical system means essentially it's a kind of a tightly coupled communication as well as the computation. So we are sensing the environment, that's the physical world we are sensing, okay? And then the sensed data goes to the computing unit. That computing unit takes what action to be taken. It uses its intelligence and provides a decision. Again, the control goes back to the physical world. Okay, so it's kind of a loop from the environment and then to the control unit, and then again back to the environment. Okay, so we are sensing what is actually happening in the physical world, and then we are passing that data to the controller, and then controller, based on the input data, it takes a decision what action to be taken in the next time step. Okay, so again, this action goes to the actuator. So this is a kind of a control loop for the cyber physical systems. So at a high level, it is the combination of digital sensing, computation, and communications. Okay, it's a direct interaction with the physical world. Now we will move to the automotive cyber physical systems. So in case of the definition, whatever we have seen, let us fit the definition with respect to automotive system. For example, in automotive system, we have multiple applications. Okay, so here the automotive car, it interacts with the real world environment, right? So in car also we have an environment. In that environment, whatever the observations we take are sense, those observations goes to the car controller unit. That controller unit takes a decision what action to be taken for the next time step. Okay, so first we will sense the environment. Again, it goes to the car's control unit, and the control unit takes a decision what needs to be done for the specific action. Okay, so for every sensing, there will be a control logic will be executed, and there will be corresponding action will be taken. Okay, so here in automotive systems, we have so many applications. We are trying to list some of the applications. For example, adaptive cruise control, automatic braking, electric power steering, and then this airbag deployment. Okay, so likewise in automotive cyber physical systems, we have so many applications. Let us take a close look at the one of the applications. For example, let us take the look at the adaptive cruise control. So the purpose of adaptive cruise control application in automotive is that it used to maintain a safe distance between the current vehicle and then the lead vehicle. For example, if you are traveling in this vehicle, you need to maintain a safe distance with the the preceding vehicle. Okay, so this is the actual distance between two cars, and this is a safe distance that needs to be maintained to avoid any catastrophic consequences. This is a safe distance. It's a recommended one. So that is already predefined settings. Okay, available. So this adaptive cruise control objective of this application is that it needs to maintain a safe distance between the preceding vehicle and the current vehicle. Okay, so this over the period of the traveling, this distance will vary. This is not a fixed one. This actual distance will keep on vary, and then it's the adaptive cruise control applications action to maintain the safe distance. Okay, so this adaptive cruise control is one of the options available in the ADAS options in the modern cars. Okay, so this is at a high level, this is the application overview. Suppose if we come to the actual block diagram on how it is handled, So what is happening? So we have 4 wheels, right? From all the 4 wheels, we will try to get what is the current speed from the both the right side wheel and then the left side wheel and then the front and rear side. Okay, from all the wheels, we need to first get the current speed. What is the current speed of the vehicle or of your own vehicle? And then we have the preceding vehicle, right? From that preceding vehicle, we need to understand what is its distance and what speed it is traveling. Okay, so similarly, you have to get obtain the yaw rate from the speed information. Okay, so using this all this input information, now you are trying to compute what is the desired speed for your vehicle, so that you can maintain a safe distance between the current vehicle and then the preceding vehicle. Okay, so this whole part, the first beginning part, is a sensing part. Okay, so you are sensing the environment to understand what is your current speed and what is the preceding vehicle speed and then distance. Okay, this whole sensing part you are feeding into the control logic. Okay, this control logic executes within the car. Okay, so this control logic decides what is the current speed and then what is the desired speed you need to operate your vehicle, so that you can maintain a safe distance. Okay, so after taking all the decisions internally, again it goes back to the actuation units. Okay, so finally it has to again go to the vehicle speed only, right? So this actuation unit will apply the control decisions taken by the controller in the car. Okay, so at a high level, we have the adaptive cruise control containing the sensing part, and then the computation part, and then the actuation part. Okay, this is a high level block diagram of adaptive cruise control application. Now, as we discussed earlier, an automotive cyber physical system contains multiple such applications. Adaptive cruise control is one such application. So for example, we have a traction control. So the purpose of the traction control is that we need to maintain the vehicle stability. Okay, so in the slippery road conditions also, we need to maintain the traction, the vehicle stability. So for that, it takes the vehicle speed. Again, it takes all from all the 4 wheels, it takes the speed and also the yaw rate it computes. Based on this analysis, it decides what speed needs to be applied for the vehicles. Okay, so again, this is the sensing part, and then this is the control part, the computation part, and then this is the actuation part. Okay, so similarly, we have electric power steering. So there are multiple such applications, and each application at a high level, we can see that it can be represented in a block diagram fashion. And in each block diagram, we can clearly demarcate what is the sensing part, what is the computation part, and what is the actuation part. Okay, so this is a high level block diagram. So from application, we now came to the block diagram. From these block diagrams, we can easily convert them into a task graph. Okay, this is a each corresponding to each block, and then the arrow marks, the dependencies. The dependencies depict that first the previous action first needs to be completed, then only the following action can start. Okay, that is the precedence constraints enforced by these arrow marks. Okay, so that is exactly represented in terms of a task graph. So these task graph is a special kind of a task graph called a directed acyclic task graph. So in case of a directed acyclic task graph, there is no loop back to the initial or any other nodes the DAG. Okay, so the information flows from left to right. That is called a directed acyclic graph. So we can represent every application in terms of a block diagram, and every block diagram can be represented in terms of a directed acyclic task graph. Okay, so in case of automotive application, we have so many applications, and each application can be modeled in terms of a task graph. Okay, so this is an overview of this automotive cyber physical system and how to model the applications in terms of a task graph. Okay, so far we have seen the application view of the automotive cyber physical systems. So now I'm just trying to abstract whatever we have discussed so far. Any application, we can see that it will have a top layer and middle layer and bottom layer. So in case of a top layer, it is kind of sensing the environment. It's a cyber physical system. It has to sense the environment, what is actually happening in the environment. That information it has to gather. Okay, after gathering that information, this information has to be fed into the middle layer that actually contains the intelligence part. Okay, that intelligence, what it does, it takes the input, it knows what is the desired output. Okay, and it does the course correction. For that course correction to happen, you have to again do the actuation, right? So it provides what is the control, the amount of control that needs to be applied for the actuation unit, so that the desired output will be obtained. Okay, so we have at a high level, we have the DAG. These directed acyclic graphs can be layered fashion. We can split. The top layer will be a sensing part, middle layer will be the computing part, and then the bottom layer will be the actuation part. Okay, so the task graph, the directed acyclic task graphs can be represented in terms of sense, compute, actuate task graphs. At a high level, it's a sensing, computing, actuating. Okay, this is a high level abstraction of the applications that are going to be executed in the automotive platform. Okay, so far we have seen what is the applications perspective. Now let us move towards the computing platform point of view. Okay, so let us consider the brief diagram of the automotive car. So in automotive car, we have multiple computing units. Okay, so we have this is a abstract representation of the car. So it has multiple. For example, this is a one processing unit, and then for example, this is another motor is present, and then for wheels we are attached with the actuator networks. Okay, so if you take the car, it has multiple control units and multiple, for example, multiple sensing units as well as the control units and then the actuation units. Okay, so these each units are kind of a distributed within the car. Okay, the distributed means this is not physically located together. For example, sensors we have attached with each wheel. Okay, so the sensors anyway will be in the distributed fashion. So from the sensor, from the wheel sensor, we are collecting the data that goes to the centralized the processing unit. That processing unit takes a decision what control action we need to apply in the next time step, and then that action also again goes back to the actuators. Okay, so for example, if you take the modern automotive cars, it contains almost 70 to 80 processors. Okay, so the, for example, this whatever the high end vehicles, those are heavy. The cost of the vehicle is mainly determined by the features it supports. Okay, so the number of features it supports, again it will have the direct impact on the number of processing units that needs to be present in the platform. Okay, so in automotive car, in the modern vehicles, it almost contains 70 to 80 electronic control units. They are briefly called as a ECUs. Okay, so this is a high level view of the hardware components in the automotive systems. Let us go into the deep details of the components. Okay, so if you come into the individual hierarchies, as I mentioned earlier, so the processors in the automotive units, automotive systems called electronic control units. For us, we are familiar with the term processors. So here it will be called electronic control units. There are multiple ECUs. Okay, and this we have discussed that these ECUs are distributed across the automotive system. Okay, so they are not sitting in the same place. Okay, so these each application will be able to, means this each processing units actually contains they are going to process certain information, and then they are going to gather the information from sensors and they are going to process it. Again, this information has to go back to the actuators. Okay, so here how these ECUs are connected. So there is a network, again this here internal to the automotive system, there's a network topology. Okay, so when it comes to network topology, we ultimately know that, right? So we have different types of protocols. In case of an automotive system, we have a LIN protocol, and then the control area network protocol CAN bus, and then we have FlexRay bus, and then we have automotive Ethernet. Okay, there are different types of networks and different types of topologies how we can connect these ECUs. Okay, so we have a automotive system. In automotive hardware platform, we have set of processors, and these processors are connected using different bus protocols and the different topologies, and each topology may execute different communication protocols. Okay, so for example, first we discussed about the LIN. So what is the purpose of using different protocols, right? So we have different requirements. For each specific requirement, we will use a different the respective protocol. For example, LIN is one of the protocol. So the LIN's the data rate is 20 kbps approximately. Okay, so this can be used in a master slave topology, and the corresponding use cases. It's used for the seats, mirrors, and windows control. Okay, so this 20 kbps may not be enough for the other applications, right? So each application will have its own demand. Okay, so we have a different protocol called CAN-FD. Okay, that supports up to 5 Mbps. Okay, so this operates in a master slave. It's kind of a multi-master mode. So this is kind of event triggered systems. Okay, so whenever certain event happens, how to process that data. So in such a scenario, this CAN protocol will be used. Okay, here example is the airbags and the diagnostic systems and engine control. Apart from that, we have this FlexRay. FlexRay, if you see, it has almost double the data rate of CAN bus. Okay, and this is operating in a time triggered fashion. Okay, so in the CAN bus, it's event triggered. Whenever certain event happens, then only the message transmission will happen. Okay, otherwise this bus will be idle only. Here the flex rate, it will operate at this 10 Mbps rate. For every 10 Mbps, every cycle there will be a periodic messages will be shared across the ECUs. Okay, so that information will be carried periodically. So for example, this is used for this brake by wire and steering applications. Okay, apart from that, now whatever the Ethernet we are using in our desktop applications, now those also now going into the automotive systems. Reason is that now we want the infotainment also into the cars. Okay, when you have the infotainment and then we have a lot of applications, they need a huge data rate, right? So now we have huge amount of data for the streaming. Okay, for if you do streaming, we ultimately know that this 1 Mbps or 20 kbps are not sufficient at all. Okay, so then ultimately we will end up in this buffering and then the streaming, right? So to avoid that, so we need to have the higher end data rate support. So that is why we have the Ethernet. So these are the different types of protocols, and they support different types of data rates, and then they have different types of topology, and they have different types of use cases. Okay, so far we have seen that in automotive platform, it contains electronic control units, and these control units can be organized in a different topology, and these buses, whatever is there, they can follow different types of protocols. So those protocols and their categorization we have discussed so far. Okay, apart from this architecture, whatever we have seen in the past, okay, in the previous, compared to the past decade, if you go, so each application, whatever the application we discuss, take the adaptive cruise control or a traction control or a wheels, the power steering, all these applications are executed in a dedicated ECUs. Dedicated means in one ECU we will execute only one application. Okay, so this is called a federated architecture, where so each ECU will always be dedicated for one particular functionality. Okay, it will execute one functionality and it will just wait. It will just will be in the idle mode. Okay, so likewise, each functionality distributed. Okay, so if you go in this fashion, what will happen for each functionality? If you start dedicating one ECU, suppose the car suppose go to the next generation car. If you want to add one particular feature, we will deploy one extra processor. Okay, so each feature we want to supply, each feature that you want to support, you will ultimately end up in keep on adding the additional resources. So adding the resources mean you are increasing the cost of the vehicle. Okay, so indirectly, though this allocation of executing the one application on one processor is simple and easy to design, but with respect to the cost of the vehicle, it has a direct impact. Okay, each resource you add, it has a direct impact on the cost of the vehicle. Okay, so what is happening in the modern vehicle, we are moving away from this federated architecture to the integrated architecture. Okay, so in the integrated architecture, what is happening, these resources are trying to utilize whatever the unused capacity of these processors, because this processor executing only one application and remains idle forever, right? Until the application again comes back, it remains idle. So this in between idle time, we are trying to skews. How we are trying to skews? We are trying to co-schedule all the multiple applications on the same processing unit. Okay, so this is a integrated architecture where multiple applications co-execute on the same ECUs. Okay, so this is the integrated architecture where we are trying to maximize the resource utilization. Okay, but what is the ultimate impact is that now the design is complex. Okay, because when multiple applications execute together, they need to communicate also, right? So now the message transmission and what time you have to schedule these applications on the architecture, the underlying platform, these are the design choices will become complex. Okay, so so there's a trade-off which you can clearly see. Okay, in a federated architecture, the design logic is very simple. Okay, but it will have the cost of the vehicle increase. If you come to the integrated architecture, you are saving in the cost of the vehicle, but the design mechanism, if you are trying to maximize the resource utilization, but the design, right, whatever the scheduling, that becomes challenging. Okay, so these are the kind of a paradigm shift from the federated to the integrated architecture. So far we have discussed what is cyber physical system and how we moved from to the automotive cyber physical system. In automotive cyber physical system, we have discussed different types of applications. In those use cases, how they can be modeled, right? So each application, how they can be represented in terms of a sensing, computing, actuating task graphs. Okay, So then first we discuss application, then we come to the hardware architecture. From hardware architecture also we discussed the ECUs and then the different types of network topology and different types of communication protocols. Then we come to this federated architecture and to the integrated architecture. So moving forward, now we are very discussed clearly about the application model and then the underlying hardware platform. We will move how to schedule this application on this underlying platform. So that will be our next discussion. Okay, so I'm just summarizing the problem statement now. So application model is we are trying to represent the application in terms of a task graph. So DTG is directed acyclic task graph. Okay, and each application, see, some applications are real-time applications. So the term real-time means it has to be completed within this stringent timeline, the deadline associated with that application. Okay, so if you execute the application and if you provide a correct result, but if you are providing the correct result after the deadline, that does not have any usefulness. Okay, that is the real-time systems definition. So if you see this application, these applications, each DTG has its own deadline. Okay, and then these applications is going to be executed on the platform containing different heterogeneous processing elements. Okay, these ECUs has a different capacity, or means each ECU has a different processing capability. These ECUs can be a CPU, can be a FPGA, can be a GPU. Okay, so each one has its own processing capacity. That is why they are called heterogeneous processing elements. And then we have a heterogeneous shared communication bus. What is the reason to call heterogeneous shared buses? We have different bus protocols and different capacity of those protocols, right? So that is why the platform is also kind of a heterogeneous, and then the application going to be executed is a kind of a real-time application. Okay, so now the what we need to determine. Okay, so this application going to be executed on this particular platform. We need to determine which task will be executed on which processing element. Okay, that allocation we need to do. Similarly, the messages are going to be transmitted, right? So which message will be allocated on which particular bus? So that is again allocation strategy. Okay, after allocating these tasks to processor, message to buses, we need to come up with a temporal scheduling. So temporal scheduling means at what time instant they will start executing. For example, you have allocated a task to a processor. You need to decide at what time step the task will start executing on that particular processor. Similarly, you have assigned the message to a bus. At what time instant that message will start its transmission on that particular bus. Okay, so these are the answers we need to find. So our input is application, and then we have this platform. Okay, what we need to determine the schedule. Okay, so currently the objective of the first problem statement is that we need to come up with this assignment and then the schedule, such that we need to schedule them as fast as possible. Okay, so we need to ensure that these messages or tasks, whenever they are ready, we need to ensure that they are scheduled. Okay, so that the overall schedule length is minimized. That minimize the schedule length should satisfy this deadline requirement associated with the application. Okay, so in the current discussion, we are dealing with the scheduling of single application. Okay, modeled as a DTG going to be executed on the platform, and these are the requirements which we are going to compute with the objective of minimizing the schedule length. Okay, so this is our problem statement now. Coming to the solution approach. Okay, so as I mentioned earlier, for example, digital design, we have the Karnaugh map and then the Queen-Mikulski approach. Okay, so for the same problem, we have different approaches, right? The purpose is that the reason for having multiple approaches is that we want to solve the problem. Sometimes we want to solve the problem in a fast manner. Okay, we don't have enough time, so we want to solve it quickly. Okay, in that case, what will happen? We will go for a heuristic. Okay, that is, for example, K-map. We want to quickly solve the problem of finding the Boolean expression with the minimal sum of the min terms. Okay, and then if you come to the Queen-Mikulski, which will provide a best solution, but problem is that we need to iterate over all the combinations. Okay, so if you have a time, you can always go for this Queen-Mikulski because it will provide the best solution. Okay, so for this problem also, we are having optimal approaches as well as the heuristic approaches. First, let us discuss the optimal approaches. Okay, so in optimal approaches, typically in optimization, we use integer linear programming. Okay, so in integer linear programming means it's like our maybe I just provide a brief background on the integer linear programming. For example, we might have solved the equations like x1 plus x2 or x3 in the Grammar's rule. We will try to solve the sum of systematic equations and try to come up with the equations the values for x1, x2, x3. Okay, using that's a typical the 12 standard equations whatever we used to solve. Okay, there the equations will have we need to solve the equations and come up with the solutions for x1, x2, x3. Okay, so here we need to model all the constraints in terms of such kind of equations. Okay, so we need to model what are the constraints associated with the application and platform. We need to model everything. Okay, and then there's a standard solvers we no need to solve. For example, the grammar's rule means we will get the equations and we know the rule how to solve it. Okay, we will solve it step by step. Okay, now we have all the solvers which are capable of solving all these equations. So our job is that given the application and then the problem statement, we need to encode the problem statement in terms of constraints and objectives. Okay, in the format that integer linear programming expects. Okay, so here the objective is we need to minimize the overall schedule length. What are the constraints we need to satisfy? We need to ensure that each task starts at the unique time step, and then in the platform, what it imposes, platform has a limited number of resources. We don't have an infinite amount of resources. Okay, so while scheduling these applications, we need to ensure that the resource constraints associated with the platform is satisfied. Okay, if there are only two buses or 4 processors available in the platform, so at any given point of time, we cannot schedule more than what is available in the platform. Okay, even though we have 10 tasks ready for execution, we have only 5 processors in the platform. That means out of 10, we can only execute 5 ready tasks on the available processors. Okay, those what resource constraints also we need to satisfy. And then dependency. Dependency means each application mandates that only when the previous step is completed, then the next step can start, right? So we need to ensure that dependency constraint also satisfied. For example, if you have 5 processors, only two tasks are ready for execution means you cannot go and fetch other tasks to execute. Reason is that it may have the precedence constraints. For example, it first needs, it cannot be executed unless its predecessor has completed the execution. Okay, so this is kind of a different types of constraints we need to satisfy while while trying to minimize this subjective. Okay, so here also with respect to ILP, there are different styles of modeling this problem. Okay, one of the style is the time step based approach. Okay, at every time step, so we have the deadline for this application, right? So we will come up with a decision variable xirt. So here I means the ith node in the task graph. Okay, the task graph contains multiple nodes, and for each node we need to find at what resource it will be mapped and at what time step it will be executed. Okay, so the decision variable will be xirt. So it's a kind of a 3-dimensional decision variable which takes a value either 0 or 1. When it will take value 1, if you assign the ith task node on rth resource, that resource can be a task, can be a processor or a bus. Okay, and what time step? Okay, that is a t we are discussing. Okay, if it is assigned to a specific time step, that will take a value 1. Otherwise, it will take a value 0. Okay, this is one style of modeling this problem. Okay, so that's another style called non-overlapping approach. In this case, we are not bothered about the time step. We are having a 2-dimensional variable. So it's a xir. So ith task or a message at which resource it is going to be mapped. So that is only 2 dimension we are restricting, means we are limiting. So compared to the previous approach, it's a 3-dimension. We are telling what which task graph and what resource and at what time step it is going to be executed. Here it's a 2-dimensional modeling where which task node in what resource it is going to be executed. But we are introducing another single dimension variable. Okay, this single dimension variable will tell at what time this particular ith node will start. Okay, so we are decomposing the 3-dimension variable into a 2-dimension variable and one single dimension variable. Okay, this is kind of different style. For this problem, we have derived 2 different approaches. One is called this explicit time step based approach. Another is a non-overlapping approach. Okay, I'm not going to further details of how mathematically this model. I'm directly going to the results of this problem. Okay, so you can, so if you come up with this approach, there are 2 approaches. Why we are coming up with the 2 approaches that because each modeling has its own advantage and disadvantages. We want to solve the problem as fast as possible. Okay, even with the ILP approach. Okay, so for the adaptive cruise control application, whatever we discussed, right? So consider the platform consisting of 4 processors and 2 buses. Okay, so for that kind of a platform, if you are trying to schedule this adaptive cruise control application, which we have seen in the beginning of this presentation. Okay, so that was containing multiple task nodes, almost 20 task nodes, and then it has around 11 message nodes. Okay, these are numbered from 1 to 31. Okay, so we need to schedule these task graphs, the task as well as messages on the system containing 4 processor and 2 buses. This is the example system configuration, okay, for the illustration purpose. Okay, for this system configuration, if you use this ILP explicit time step based approach, we are coming up with almost 6,40,800 equations. Okay, those many number of equations we are coming up with. Okay, then we have a standard solvers to solve it. So if you solve it, almost it takes 8 hours to solve this problem. Okay, if you just feed this single application for this specific system configuration using the ILP explicit time step approach, it takes almost 8 hours to come up with the optimal solution using the simplex optimizer. Okay, same problem statement, we have modeled it differently, right, using the non-overlapping approach. Here it generates only 5,000, approximately 5,000 constraints, and it can solve this problem, same problem, in 2 hours and approximately 20 minutes. Okay, so one of the reason is that you can see that the decision variable, once you, even though this is a single decision variable, it's a 3-dimensional variable. Okay, here we have, even though the 2 decision variables, we have one 2-dimensional variable and one single dimensional variable. Okay, once you expand the dimensions, the search space will increase. Okay, to give the insight on the search space, for example, let us go to the task graph. Okay, for example, we have the task graph, right? So this task graph, for example, the node 20. Okay, once the node 20 completes, for example, if you have 3 nodes ready for execution, okay, and then we have 2 processors. Suppose the platform contains 2 processors. Okay, the choices will be 3 choose 2. Okay, out of these 3, we need to choose 2. Which 2 you will choose, right? So the subset selection is kind of a combinatorial optimization problem. Okay, so this combinatorial optimization problem, if you try to find the optimal solution, it will search for the entire solution space. Okay, if it is a 3-dimensional solution space, it will have more number of solutions to explore. But if you come to the 2-dimensional solution space, the search space will be smaller. That is why this ILP NC is able to generate a solution much faster compared to the 3-dimensional solution space with ILP ETR. Okay, so far we discussed about the optimal approaches. Okay, just to see, for a small example, it takes 8 hours, and then even with the optimized version, we are still taking 2 hours. Okay, this may not be feasible for large scale application. Okay, this is for even for toy example, we are getting this much amount of time. Okay, so let us see this one. For example, the number of task nodes we have seen totally 30. Okay, for 30 itself, you can see that the ILP runtime. Okay, in the logarithmic plot, you see that. So it almost takes, for example, for normal examples, 4 hours may be a practically feasible one. Okay, if you are taking almost 12 hours or 20 hours to solve a problem, that is not practically feasible or relevant one. Okay, so this ILP is okay. Okay means it's again a trade-off. Okay, ILP provides the optimal solution, but it takes huge amount of time. Okay, so like this K-map and then the Queen-Minkowski, now also we need to come up with a heuristic. Okay, so one such heuristic is the CCTMS. Okay, which attempts to solve the same problem within 5 milliseconds, but it is not guaranteed to provide the best solution. Okay, that is a trade-off. Okay, so now we will go into the details of this CCTMS. Okay, so coming to this execution. Okay, so when you are developing this, in case of ILP, we have seen that we are modeling all the system input and then the constraints in terms of objectives and variables, the decision variables. Okay, now it's a heuristic. Okay, in heuristic, we need to explicitly mention at what time step which application will be executed and which resource it will be executed. Okay, for example, let us consider 2 processors. Okay, and there is a shared communication bus. Okay, in processor 1, there are 3 tasks going to be executed. Similarly, in processor 2, there are 3 applications going to be executed. Okay, if you don't schedule them properly, when both of these processors trying to exchange a message via the shared communication bus, what will happen? There will be collision happening, right? So we need to ensure that there is no collision. So the scheduling algorithm, whatever we are telling, right, the heuristic, that should be capable of handling this collision. Okay, so when you have multiple applications executing across different processors and there is a shared communication bus, we need to ensure that this, whatever the heuristic we are developing, that should be aware of the underlying platform configurations and ensure that there is no collision. Okay, so that is how, based on these constraints, we come up with a heuristic called a CCTMS, which schedules these applications across the available processors. Okay, and it takes care of this collision also. Okay, it's a kind of contention cognizant task and message co-scheduling. Okay, so this is a overview of CCTMS. Let us go into the details of CCTMS. Okay, first what it does, for each application graph, we know that there is a topological ordering. Topological ordering means we cannot violate the precedence constraints, right? So by taking care of the precedence constraints, how do you rank each node in the task graph? Okay, so you are given an application. That application, for example, adaptive cruise control, that is modeled in terms of a task graph. The task graph contains multiple nodes and edges. Okay, each task node, we are trying to come up with a priority. Okay, so there is a rule to assign the priority. So the first phase is about assigning the priorities for each node in the task graph. Okay, once you assign that priority, so the highest priority node will be taken for assigning it onto the processing platform. Okay, so you will try to see there are a set of processors, P1, P2, P3 is a processor, and then there are buses, bus 1 and bus 2. Okay, so take the task and then assign it to the processor where it can be executed in a fast manner. Okay, in a fast among all the processor where it can finish faster. Okay, so take the processor and map it here. While mapping, you need to ensure that you are trying to schedule a task as fast as possible. Okay, so among you have multiple choices. You schedule the task on a processor where it can be executed faster. Okay, so this is a high level overview. Similarly, we will try to schedule the messages on the buses so that there is no contention. Okay, this is a high level overview of the CCTMS algorithm. So there are three phases. First is upward ranking, where we are trying to assign the priorities for each task node, and then we are trying to map it to the processors on the buses. And then while mapping, we are trying to ensure that you try to assign the task to the processor where it can be executed faster. Okay, this is an overview of this algorithm. Here you can see that first step itself, you are coming up with the prioritization. Okay, here we are not exploring all the combination. For example, if there are 10 task nodes ready for execution and there are only 5 processors available, means the choice will be 10, choose 5, right? Here we are not exploring all the combination. This heuristic simply crudely assigns a priority. Okay, so in case of optimal ILP approaches, it explores all the combinations. All this choosing 10 out of 5, it will explore all the combinations. Okay, but here we are simply avoiding that exploring the entire state space. We are just limiting to one specific combination. Okay, that is how this heuristic is developed. Then let us compare the result. Okay, for the same, this is now I'm moving to the adaptive traction control application. For the adaptive traction control application, if you schedule the application using the ILP, whatever we discussed, the optimal approach, for that it provides a schedule with a make span of the make span means the schedule length from the start to when it completes. This is a starting node and this is a sync node. It completes almost 1800 microseconds it takes from the start. Okay, the schedule length is 1800 microseconds. It has taken almost 2 seconds. Okay, this is a very small task graph with almost 10 nodes only. Okay, and it is scheduled on a 2 processor and 2 bus systems. For this, the make span is 1800. Make span means the schedule length, and how much time it has taken to find this solution? Only 2 seconds. Okay, now it comes to a CCTMS heuristic. Okay, CCTMS, we know heuristic, so it does not explore all the combinations of the input and then output. Okay, so it provides a one crude solution. That solution make span is 1895. Okay, but the runtime, if you see, it is 50 microseconds. Okay, so there is a trade-off between the optimal approach and the heuristic approach. In optimal, we are trying to get the best possible make span, that is 1800 microseconds. No other algorithm can do better than this. That is the optimal, right? That's 1800 microseconds. Coming to the make span of the heuristic algorithm, that is 1895. But you see the runtime, it is taking 2 seconds, but it takes only 50 microseconds. Okay, so there is a trade-off in the solution quality and then the runtime. So it depends on what design choice you have. If you have enough time to come up with a solution, use ILP. If you don't have enough time, you want a quick solution, use the heuristic to come up with a solution. Okay. So far we have seen the single scheduling of a single application on the heterogeneous shared bus based platform. Okay. So now we are coming to this triangle of heterogeneity, time, and energy. Okay. So far we did not consider the energy aspect into the problem at all. Okay, so if you see the platform, we have a heterogeneous platform. Heterogeneous means we have multiple ECUs. That ECUs can be a processors, for example, Intel or ARM processors. Okay, and then we have a GPUs, can be Nvidia or AMD GPUs, and then the FPGAs. Okay, so each, for example, we have a deep learning accelerators also. So each application may start the execution on the on a CPU, and then it will be offloaded to the GPUs or FPGAs. After completing the computation, the results may again come back to the CPUs. Okay, so this is a one platform. This platform also has a limitation. Okay, so you cannot always keep all the computing units or ECUs in the platform. Okay, if you keep on operating, what will happen? Ultimately, you are consuming the energy. Okay, if you keep the system on, you are consuming the power. Okay, and in automotive, you know, right, it is not connected to any main power line. It has its own battery. Okay, so the battery means battery has a energy, the battery also has an energy limitation. Okay, and then whatever the application going to be executed on this platform has a timing constraint. Okay, you cannot switch off half of the computing unit and use only the half of the computing capacity. Okay, what will happen ultimately? If you cannot meet the deadline, there is no use. For example, in case of adaptive cruise control, it has to take the decision within 100 milliseconds. Okay, that is a prescription from the ISO 26262 standard. So for each application, there will be a fault tolerant time interval. Okay, that's a FTTA budget. Okay, within that budget, it has to react. Okay, if it takes more than that time, the consequence will be catastrophic. So catastrophic means it will be a huge damage to a vehicle, or maybe a loss of life also to the humans. Okay, so this is a triangle. If you see, we have a resources. You cannot keep all these resources always on. Okay, if you keep always on, what will happen? It will going to drain the battery. Okay, but what will happen? You need to come up with a judicially. You're going to come up with a scheduling approach which takes care of the energy budgets as well as satisfies the timing constraints of the applications. Okay, so now let us look into the energy aspect of this problem. Okay, to understand the energy aspect of this problem, first let us understand what is power. Okay, so power means we know, right? So it has a static power and then the dynamic power. So static power means when you keep the system on, it's always there will be some power will be consumed. Whether you are running the application on the CPU or not, if you switch on the system, the CPUs will be on, there will be a static power will be consumed. Okay, here we will focus on the dynamic power. Dynamic power means you are executing some applications. So transistors in the CPU getting transition from on state to off state, from off to on. Okay, whenever this transition happens, correct, that alpha is a transition activity and C is a capacitance corresponding to that. Okay, and then what is the voltage in which it is operating, right? So the dynamic power is proportional to the square of voltage, operating voltage, and linearly proportional to the operating frequency. Okay, so the dynamic power of operating the processors or a computing platform is, each processor is CV square F. Okay, and from the power, if you come to the energy is a kind of area under the power, curve, right? So if you see over the time period, whatever the amount of duration you are operating multiplied by the power, dynamic power, that is the energy. Okay, so if you take the modern processors, they have the something called the DVFS. That means dynamic voltage and frequency scaling. So each processor provides a knob called DVFS. So it will have a set of frequency and voltage combination. For example, if you see this table, we have this voltage and frequency. So if you operate the system at 1 voltage, you can operate at the 3 gigahertz frequency. Okay. Similarly, there will be set of prescribed frequency. For example, if you take the Intel processor, it will have at least 4 to 5 voltage frequency levels. It may be having 0.8 voltage and 2 gigahertz, or maybe having 0.5 voltage, 1 gigahertz. Okay. And then this is called a DVFS levels. Okay. Consider the voltage and frequency level for this 1 voltage and then 3 gigahertz. So if you apply this formula, the power output will be 3 units, right? The voltage is 1 and then the frequency is 3 gigahertz. So almost power is 3 units. And if you operate it for one time unit, what is, so if you operate it for this energy per task will be 1 time unit. Okay. I think it's a, okay, I'll cross check, but it is, if you operate for this time unit T, so it will be kind of 1 time unit. This is considering if you are operating the voltage and the frequency at this particular level, this is the power. Okay, but if you lower the voltage, the 0.8, and the corresponding frequency is 2 gigahertz, the corresponding voltage is the power you consumed is decreasing from 3 units to 1.28 units. Okay, and the correspondingly, what is the energy consumed? It will become 0.64. Okay, so if you are changing the voltage, means if you are decreasing the operating voltage and then the frequency, you are saving the power as well as the corresponding energy. Okay. Now let us come to the task execution perspective. Okay, how you can lower the frequency, right? So this is, for example, you take the task. If you are executing as fast as possible, that means what is the maximum frequency and maximum voltage available in the platform. If you are operating for that particular voltage and frequency, you will complete the execution quickly. But you have a deadline for the application, right? You are completing much early. Okay, so the slack is the difference between the deadline and the completion time of the application. Okay, so you are almost keeping this much amount of time idle. Okay, instead of keeping this way, okay, what you can do, you can operate the processors in a DVFS fashion. Okay, instead of operating at the maximum voltage and frequency, you select the specific voltage and frequency level so that the application completes on time but operates at the lower voltage and frequency level. In that way, the energy consumed will be much lower compared to operating the processors at the maximum frequency and voltage level. Okay, this is called the DVFS approach. But here also again, the already we have seen that the problem, the whole problem is about mapping the application to the platform. Application has a certain demand, but the platform is containing the limited computing resource. Okay, limited computing resources means set of limited number of ECUs and then the buses. Okay, now we are adding one more dimension to this problem. What is the dimension? It's a DVFS. So what voltage and frequency level you are going to operate these ECUs, you are adding one more dimension to this problem. Okay, so far we have discussed that one application how to schedule. Okay, but in reality we have seen that there are so many applications to be executed on this platform. Okay, so each such application will be modeled in terms of a directed acyclic task graph. Okay, and each application has its own period. It will come periodically and it needs to be executed within the stipulated timeline. Okay, so we have multiple applications and each application executes in a periodic fashion and each application has a certain deadline. Okay, so when you are preparing a schedule, what we are going to do is that we are going to prepare the schedule for the hyper period. Hyper period means it's the least common multiple of each individual periods. For example, each application, for example, you take the application 1, suppose its period is 10 and the second application period is 20, means if you come up with a hyper period, the hyper period will be 20, but the application one will come for 2 times in the same hyper period of 20. Application 2 will occur for only 1 time in that hyper period. Okay, so hyper period usually in the automotive system, the schedule will be generated only once for the entire lifetime of the platform. Okay, entire lifetime of the automotive system. For that, they will expand they will try to, for each application, they will try to come up with a schedule. That schedule will be prepared for the hyper period. Okay, the hyper period is the least common multiple of each individual application's period. Okay, so this is kind of a timetable you are coming up with. That timetable contains whenever application comes, where it needs to be executed, okay, and it needs to be satisfied the deadline. All this will be taken care by this particular schedule. Okay, so the problem is that we are given a set of multiple applications and we need to schedule them on the automotive platform while satisfying the deadline constraints as well as the energy budget. Okay, so we're trying to minimize the make span. Okay, we need to try to minimize the make span as well as meet the energy constraints. That is what this Safla does. Okay, so Safla also it operates in 3 stages. So first stage is you are having multiple applications, right? So in multiple applications, they may come in multiple times also they will come. Okay, so in such a case, whatever the CCTMS heuristic we have seen, that will be extended for this task prioritization for each individual application. For each individual application, you need to come up with a priority, and then for each node in the application will be assigned a particular priority. So this will be a global priority scheme considering all the applications together. Okay, once you assign this priority, next step is co-scheduling the tasks and messages. So we will take each task and message and we will try to schedule them on the available processor and buses. Okay, after scheduling it, we need to ensure that the deadline is satisfied for each application. Okay, then we will try to see the gaps. So we come up with the initial schedule. Initial schedule means we map the tasks and processors to the, we map the task to the processor, we map the bus messages to the buses. Okay, after mapping, we will try to see the gaps. What are the gaps available? We need to come up with adjustment adjusting this slides, means we need to slide or slightly change the DVFS level so that the energy will be minimized. Okay, so it operates in 3 phases. First, come up with the priority for each task node and then schedule them on the platform. After scheduling, you try to see the gaps in the schedule. By seeing the gap, you try to extend the execution. How do you extend the execution? Lower the operating frequency. By lowering the operating frequency and voltage, what we are trying to do, we are saving the energy. Okay, so this is kind of a 3-stage problem. We are trying to co-schedule multiple applications on the platform by satisfying the deadline. After satisfying the deadline, we are trying to squeeze out whatever the slack available in the system to lower the frequency. Ultimately, we are saving the energy. Okay, this is a Safla. That is the objective or the title of this presentation. Okay, so far we have discussed multiple approaches, right? So first is the optimal approach. Okay, first algorithm is called ILP, that is an optimization approach. For that, we discussed how to schedule a single application. Okay, there the objective was make span, and the make span has to satisfy the deadline constraint. Okay, and then the contention means we know that we cannot arbitrarily schedule or schedule the messages on the buses, right? We need to ensure that the constraints of the platform also taken care. Okay, so in that way, ILP is actually good. Good means it provides an optimal solution, but the running time is totally unacceptable for real world use cases. Then we come up with the heuristic. That heuristic is good, but problem with that is that it can handle only single DTG. It will provide a good solution, but it is not guaranteed to be the best solution. Okay, then we extended the single DTG application to the multiple DTGs. Suppose you are given a multiple DTGs, how do you schedule multiple applications together? While scheduling the multiple applications, how do you save the energy? Okay, so all these 3 aspects we have discussed. Okay, so now the future wise, if you see, not only so far we discussed the energy aspect. Okay, there are multiple aspects to this problem. Okay, we have now the reliability constraint. Okay, reliability means whenever the application is executing on the platform, maybe let me go to the DVFS slide. Okay, see, whenever this application executing on a processor, it is susceptible to the transient faults. Okay, the transient faults means, see, processors means ultimately it contains a transistors, right? So for example, if you consider flip-flop, flip-flop also what will happen, the state transition means 1 to 0 or 0 to 1. Okay, so in the typical fault tolerant scheduling, they say that, for example, the electromagnetic interference or a transient fault, due to that the flip-flop state can change from 1 to 0 or 0 to 1. If a single flip-flop changes its state, it will have a consequence on the correctness of the output produced by this task executing on the processors. Okay, so if you execute the application for long duration, if you execute the application during its execution on the processors, if one of the flip-flop state changes its states, the output will become incorrect. Okay, so you have to execute as fast as possible the application on the platform so that it is not susceptible to the transient faults. Okay, but what will happen if you try to execute the application as fast as possible? You are going to execute the application at the highest DVFS level, so you are going to consume the energy high. Okay, but if you operate the application at the very lowest DVFS level, what will happen? You are going to save the energy. Since you are occupying your execution for long duration on the processor, you are having more susceptible to the transient faults. Okay, if you execute for this much amount of duration, you have a very high chances of getting impacted by the transient faults. Okay, so if you see all these objectives are contradicting with each other. If you try to minimize the energy, what will happen? You are going to execute very long duration. Because of executing for long duration, what will happen? You are susceptible to the fault. Okay, so the reliability means you are trying to execute as fast as possible to maximize the reliability, but to save the energy, you have to execute very slow as possible, still meet the deadline. Okay, so there are so many different constraints coming into the platform because the platform nowadays is heterogeneous and there are many constraints associated with. Okay, so what are the problem we discussed? There can be multiple dimensions to this. So if you add a reliability as a one dimension, this is again a new problem statement that you can solve. Okay, and solution approach, whatever we discussed, right? We discussed the ILP approach and then the heuristic approach. So there are approaches called a meta-heuristic approach. So we can use a genetic algorithm or a simulated annealing, okay, ant colony optimization or particle swarm optimization. Okay, what those algorithms will do that they will take this kind of a heuristic algorithm. Okay, they will. So we have seen that if you see the case of CCTMS algorithm, it is providing only one rule, okay? Instead of exploring all the task to processor mapping, it is blindly come up with one approach, okay? So if you start varying this task to processor mapping, that is where this meta heuristic comes into picture. The meta heuristic algorithms will try to tweak this input combination. They will try to use the CCTMS algorithm as an underlying algorithm, but in the first stage, they will provide different priorities to different task nodes. If you vary the priority, what will happen? The schedule will vary. If the schedule is varied, means the schedule length will vary. Okay, so that is how this meta heuristics varies. The meta heuristic algorithms handles. Okay, apart from that, we have this reinforcement learning or deep reinforcement learning algorithms also. Okay, if you come to this reinforcement learning algorithm, what it will do? It will take one time. It will schedule it and see what is the priority we have given, what is the schedule we have obtained, right? So taking for each schedule, it will take the reward. By taking the reward, it will do a course correction. It will again change the priority. It will see what is the updated schedule and what is the corresponding make span. If the make span is lower compared to the previous schedule, it will provide a positive reward. Okay. Suppose the make span of the new schedule is higher than the previous schedule, it will provide a negative reward. Okay, so in that way we are providing the positive feedback and negative feedback to the your learning agent in the reinforcement learning, so that it will learn different prioritization schemes and try to come up with the best priority assignment, so that the make span will be minimized. But again, problem is that with this meta heuristics like genetic algorithm or a reinforcement learning approaches, you have to execute them for a lot of iterations. Okay, they will take lot of amount of time to converge. They may not converge within one iteration. Okay, for example, if you have seen the result for the CCTMS, right? So in case of CCTMS, the ILP was taking almost 4 hours and CCTMS was taking few milliseconds. Okay, this meta heuristic and reinforcement learning will fall within the boundary of ILP and CCTMS. They will fall because their baseline is a CCTMS, and the amount of time you give, the more the amount you give, they will provide a best solution. Okay, but it depends on how much amount of time you have to run the machine learning or genetic algorithms. Okay, so algorithms point of view also, there's a trade-off whether you want a quick solution or a best solution. And from the platform point of view also, you have objectives like energy, reliability, deadline. Okay, how do you trade off between these constraints? Okay, so this is kind of the next step where these problems can be explored further. Okay, so for this presentation, what are the references I have used, I mentioned here. Apart from that, I've taken help from this AI tools also to generate the slides. Okay, yeah, I think I covered the topic. Madam, any questions from any audience? If there are any questions?
As it is a live telecast, Rajesh, they will be, if they have any doubt, they will be posting it in the comment section.
Okay, ma'am. Okay, ma'am. Then I will take a look and then I will respond to them, madam.
Sure, sure.
Okay, ma'am. I will stop sharing here, madam.
Thank you for the wonderful session, Rajesh. It was really thought-provoking and we learned a lot.
Okay, okay, ma'am.
So I'm delighted to deliver the feedback and vote of thanks for today's generic talk series, number 41, organized by RMK College of Engineering Technology, Tiruvallur. First and foremost, I express my sincere and heartfelt gratitude to Dr. Rajesh DEVARAJ for delivering such an insightful and well-structured and highly engaging session on scheduling multiple real-time periodic task graphs on heterogeneous systems. What made today's session especially meaningful was the clarity with which the concepts were presented. He began from the basics and explained the ideas. He told the difference between the K-map and the Queen-McCluskey, where I think like the basics that he explained, the way that even the second year students could comfortably follow. He gradually took us into the domain of cyber physical systems and explained the importance of task graphs and showed how the complex real-time applications can be represented through a direct acyclic task graph. The explanation that he made about the source node, intermediate node, and the sync node clearly explained us they understand the flow from sensing to computation to actuation. The examples he discussed, especially the adaptive crucible control, helped us to connect the theory and the practical automotive application. His explanation on the electronic control units and sensing task that gave a clear picture of how modern intelligent systems operate in real time. Then he shifted, I think, from the federated architecture to the integrated architecture. It shows how the integration improves the resource utilization and reduce the cost and complexity. Another highly valuable part of this session was the explanation of scheduling. The way he presented the problem statement, he clearly showed that the challenges lies in deciding where the task should run and where the messages should allocated, and each task or transmission, how it should get begin and meet the strict deadlines. He then discussed about, he started with this integer linear programming. IL gave us a very strong understanding about the scheduling problem.